We're not going to start quite yet. We're going to wait 1 or 2 minutes, but to allow everyone an opportunity to transition from the previous link and to join from people who may be running a minute or 2 late from lunch. So we'll be getting started around 1:02.
Okay. Hello, everyone. My name is Sheng. I'm a computer scientist from Argonne National Laboratory. And in the coming 15 minutes, I'm going to present the Z-checker lossy compression assessment tool. Okay, so this slide demonstrates the design motivation of the Z-checker. So basically, the target of the Z-checker is to design a particular easy to use assessment tool that can be used to assess the compression quality, comprehensive and efficient for different data sets and users. So it is very challenging because different users may have different demands on lossy compression. Some users may require very high compression ratio, and some users may require very high compression speed or decompression speed, or particular control of the data distortion. So the checker need to cover those demands as much as possible. And moreover, the checker support 2 different execution modes, offline mode and online mode. I will detail them later on. And it also support different languages, for example, C and R, and support different I/O libraries, for example, HDF5, NetCDF are used. And also it provides different visualization ways. For example, it can generate the PDF files or visualize the results online through a web page. And it also integrates many different compressors such as SZ, ZIP, IPZ, and so on. Okay, so these slides present the design architecture. As shown in the figure here, the most important module is the analysis kernel, which contains the data property analysis module and the compression result analysis module. Okay, and through the Z-checkers API, the users can call those analysis modules from their code. Alternatively, they can also set up this server so that they can visualize the result through a web page. And the checker also provide different output formats. Okay, and moreover, the checker allows user to input different data formats. For example, HDF5 and the NetCDF, and those parts are handled by an input engine. Okay, and we have a configuration parser module, which is used to parse a configuration file based on which the users can configure different compressors and different error bounds and so on. The checker can call different lossy compressors through Libpressio, as presented by Robert this morning. Libpressio is an abstract layer which provides a uniform interface for users to call different lossy compressors very conveniently, right? So as you can see here, the checker involved a lot of different softwares and dependencies, for example, lossy compressors and Libpressios. So it is very convenient to provide a utility library or toolkit to put everything together, and this is what Z-checker installer does. Okay, so specifically, we developed the Z-checker installer, and the user can just use one command to install everything, and use another command to run the comprehensive analysis for different data files. Okay, so we present a lot of metrics supported by Z-checker in these slides. So basically, the checker allows user to analyze the data properties for the original data files, and also the compression results based on different compressors. For example, for the data properties, you can use the checker to calculate the 8-bit entropy, 32-bit entropy, autocorrelation of the data, FFT, and so on. And for the compression results, you can get the compression ratio, compression speed, decompression speed, PSNR, SSIM, and different metrics. Okay, and we also have the MPI version for all of these metrics calculation algorithms. Okay, so Z-checker provides two input modes. One of them is that the user can input two data sets, which are original raw data and decompressed data, respectively. That means, if the users have their own compressors and they already perform the compression and decompression on the original data set, they can make use of the Z-checker to perform the analysis only for the reconstructed data. Alternatively, if the user don't want to, run the compressors by themselves, they can just input the original raw data to Z-checker module, and Z-checker can automatically call different lossy compressors to perform the compression and decompression and analysis, and finally output the results for users. And also, Z-checker provides two modes, offline mode and online mode. For the offline mode, that means the user can use Z-checker to read a bunch of the data files stored in the disks and run the command to perform the compression analysis. And online mode means that the users can run the Z-checker together with their MPI applications, such that the compression results and analysis result will be generated online together with the running applications. Okay, so I then mentioned previously, we developed Z-checker dollar. It would be very convenient for user to install Z-checker and its dependencies. And also the user can just use one command, run zckeys.sh, to perform a very comprehensive analysis for the specified data files. Okay. What the user need to do is just set the error bound they want to check in a configuration file. Okay, so this slide demonstrate an example generated by Z-checker. Z-checker, after running the analysis, will generate the report in the form of PDF. This example is based on the hack dataset, and you can see that at the beginning of the report, it will show the data properties for this dataset for different fields, and also show the compression results in the following text. Okay, so we also have tested the we also have generated different Z-checker reports based on many different applications listed here. And moreover, the checker have the GPU version. We developed the cool Z-checker, and this work was published in Clutter conference last year. And specifically, we developed the very efficient GPU algorithm for each of the metrics, including derivatives, the autocorrelations, SSIM. In fact, some of them are not that easy to get very high performance. And our optimized algorithm can get 227 times speed up over the OpenMP version of the Z-checker, and the 3.5 times speed up over the simple version of the GPU version of the Z-checker, which is called MOZC. Okay. So I also would like to mention another very useful utility toolkit, QCAT. QCAT is short for Quick Compression Analysis Toolkit. So the key difference between QCAT and the Z-checker is that QCAT is much more lightweight. In fact, Z-checker, if you want to use Z-checker, Z-checker is very convenient because you just need to run one command to perform the compression analysis for a batch of the files or data sets. Okay, but some users may just want to check a particular metric, for example, the visualization or the compare ratios or the distributions. So to that end, QCAD will be more convenient because QCAD provides a bunch of the executables corresponding to different parts of the Z-checker report. For example, if you want to generate the visualization, then you can use the QCAD plus slide image command. If you want to generate the PSNR or other, for example, distribution the errors, then you can. There are also other commands corresponding to those requirements.
3 minutes, Sheng.
Okay, thank you. I think this is the conclusion. So you can download the Z-checker installer, Z-checker QCAD from the 3 links respectively. If you want to install the Z-checker, I suggest you installing the Z-checker installer. That would be more convenient because Z-checker has many dependencies, and the QCAD is the lightweight version of the Z-checker because you can use it to perform the separate analysis for different compressions and different metrics. Okay, that's it. Thank you.
Okay. Do we have any questions for Sheng regarding Z-checker or QCAD? So I have one question, Sheng. What is next for Z-checker and QCAD?
What is what?
What is next?
Oh, okay, I see. Basically, Z-checker already had the GPU versions, right? But we were developing the AMC GPU version for Z-checker, and for QCAD, this mainly target the offline usage because this is the utility toolkit, and I will mainly add more metrics if needed in the future.
Okay, Katrine, you have a question?
Yeah, very quickly, and maybe it's not so much to Sheng, but in general, this is obviously very useful. I mean, we have discussed this lots of times before. Do we know if there's a plan to have these kind of tools, if the community says, yes, we really, really want them, to have them installed on Aurora and Frontier as like easily available for everybody instead of everybody having to download packages, try to install them? Do we know this?
I'm not sure if I am the right person to answer this question. Robert, do you have any ideas? I think you probably are more expert on this.
Yeah, so I think the key answer here will be making sure that it's available in SPAC and then coordinating with the appropriate persons who's managing the SPAC installations on Aurora and some of the upcoming exascale systems. So we've definitely made a lot of progress in this area. So it's just a matter of making sure that the right set of tools that this community feels like it needs is reflected in the set of default installed programs. Thank you, Sheng, for your presentation.
Okay, thank you.
We're now ready to move on to our next presentation, which will be from Pascal Grosset on Foresight. Okay, and we can see your slides, and we don't hear you yet.
Okay, can you hear me now?
Yes, now we can hear you.
Okay, oops. So hi, my name is Pascal. I'm going to present Foresight, data analysis that matters for compression. So essentially, like, why do we need compression? Because there's a huge amount of data, and very often we need lossy compression because, like Frank mentioned before, lossless compression very often for floating point data on the arch is about like 2x. But when we do lossy compression, the important thing is how much information can we actually lose? Because like once a simulation has been run and data has been generated, what is important is scientists will use this data for like weeks, months, maybe years to continue doing analysis on the data. And so if like lossy compression can basically reduce your data set to just like one number, but this is obviously not what you want. So what you want is like, you want to be able to reduce your data set to a certain value, but then still be able to keep doing the analysis that you care about. Because if you spend like a week running a huge simulation on a massive supercomputer, and then someone has compressed your data, and your data is now like so compressed that your analysis loses all its accuracy, but does not make any sense anymore, this is not good at all. Basically, you wasted all your time spent running the simulation. So essentially, there are many different types of analysis. And very often what people will do is they will do just a visual analysis. For example, if you look at this data set, this is a NICS data set, and there's like different levels of compression here that have been applied to this data set. So when you do these different levels, and you can see that, hey, this looks okay, and I can basically use that. But a metric that scientists, that cosmologists are interested in is the power spectrum. When you look at the power spectrum for all these two different data sets here, you can see that all of them are like, this one is below 0.98, this one is like well below. And what scientists are interested is to keep the power spectrum level up to only a 1% difference. So obviously, just doing a visual analysis and looking at that does not tell you enough information to guarantee that the data is going to be good enough for an analysis. So another method that is very often used is like metrics like MSE, PSNR. They are very often used for evaluating compression, and they are good metrics for evaluating compression to know how well your data has been preserved. But the issue is the PSNR does not really correlate to the power spectrum error. For example, here, this is this data that has been generated by Darcy from Washington State University, and what this is for a NICS data set. And what he was trying to see is what is the relation between PSNR and the power spectrum error. As you see from this graph, you can't really have any correlation. So there's no real correlation between PSNR or MSE or analysis as well, or just like a visual analysis directly. Oops. So what are scientists interested in? Scientists are interested in making sure that quantities of interest are preserved. So what this means is, for example, here, this is a halo from HAC. So what they want to know is, will the mass of a halo be the same? By how much will the power spectrum deviate? And also, like, how much is the center of a halo has moved after different types of particle compression have been applied? So this is what we are going to focus on. So like Frank mentioned, there are different levels, like level 0, visual, level 1, there's the compression metrics, and then level 2 is, or level 3, sorry, is the quantity analysis of QIs. And this is what Foresight is going to focus on. It's going to focus on analysis of quantities of interest. So essentially, when you have like many data reduction options available, so what you want to know is like, what is the accuracy? What is the precision? What is the throughput that these methods give you, of course, because if you're running a compressor in situ, you want to make sure that it has a decently high throughput and it's not going to slow your simulation down. But also what you want to know is how well is the data going to be preserved? And if you look at all the different options available to you, you have like error-bound lossy compressors, SZs, GFP, MGARD, Isabella, there's a bunch of them. You can use like autoencoders, you can use sampling. So at the end of the day, there is like a massive landscape of different algorithms. And for each of like SZ, GFP, you can choose between absolute error, relative error. You can go for a huge range for absolute error and relative error until you find the correct one. So doing that is like, it's going to have a huge parameter scale that you need to see to be able to find the compressor that you actually want to use, or the data reduction method. So basically, what is Foresight? Foresight is a framework that allows us to compare different data reduction schemes. And the focus on Foresight is to evaluate how they impact different post-hoc analysis. For example, for compression, for cosmology, we will look at how it impacts halos, how halos are created and things like that. For another data set, for combustion, we are going to see that we are going to look at different like small scales and large scale analysis and see how things compare. So the different stages that you're going to do is like, so first off stage, you do like a data reduction. And after you do data reduction, you do the analysis, and then we also provide some visualization. And the analysis that we run, this is like very important. We try to work with the different scientists for who want to test the different compressions. And then we try to run analysis that kind of matters to them. We run their analysis. For example, for HAC, we run the power spectrum from the HAC database, and we run also the halo finding from HAC. For NICS, we run like Gimlet, which is the analysis suite. So we work like very closely with a scientist to be able to do that. And the aim of Foresight is to be able to bring like validation and verification to compression. Because something which is very important is the scientist needs to be able to trust the result of the data. After the data has been compressed, they need to trust that the data is reliable enough so that I can run my analysis, and my analysis will be accurate and not too much data has been lost. Okay, so essentially for Foresight, we are going to deal with different kind of, there's 3 stages. And the heart of Foresight is what is called like DRAW, the data reduction analysis workflow. So the first part is the data reduction, where we provide C-bench, which basically allows people to run different different error-bound lossy compressions. And then we can also link in with like an autoencoder, or we can link in with basically like sampling methods. So essentially, we can either pick the results from an autoencoder and then run it, or just like make Foresight run the autoencoder. So essentially, it is Python-based, and what it does, it reads in a configuration JSON file, and in the JSON file, you will specify, oh, what is the data reduction that you want to run, or just specify, I want to run only the analysis and just pick the results from this autoencoder that has been run. And then once you do the data reduction, you do the analysis, and then you do visualization. And essentially, the workflow, what it does is, once you have specified what analysis, reduction, and visualization you want to run in the input JSON file, it will go and schedule like a batch job where it will do analysis, reduction, analysis, visualization, and all components of these. And then it will just like launch batch jobs and establish dependencies between one and the other. So as example, it shown here. So essentially for Foresight, we can support like error-bound lossy compression, autoencoders, and sampling. So for Foresight, the part that does the data reduction is called C-bench. And C-bench is basically just an abstract factory pattern. So there's like a bunch of data loaders, compressors, and metrics. And for each of them, there is an interface that you can implement to add your data loader, your compressor, and your metric. So the diagram here shows the data loaders, compressors, and different metrics that are supported. So this is something that basically could be replaced by, for example, by Libpressio, and would probably achieve a better result. But in this case here, this was just something that we needed because most people want to just run some compression, and then we just decided that to add that method so that people could actually run things and then compare things. But essentially, the important part here is like this framework that allows you to specify different data reduction, analysis, and visualization.
5 minutes.
Okay. So, and then there's a visualization part. So our visualization part is integrated with Cinema Explorer, which allows you to, there's like a parallel plot here. And then in a parallel plot, you have like different types of metrics that you have tried, different types of compressors, like for example, there's loss, SZ, ZFP, and then it shows you what is a compression ratio and a bunch of other metrics that have been provided. And then the important part is for each of them, you can select and get like an enhanced view of, for example, here, this is an analysis for a combustion. So example of application, the first application that we're going to look at is turbulence. So essentially what we have is like have a 3D numerical dataset, which is like quite big. And what these guys had done is they had created an autoencoder. And they wanted to see like, oh, there's how well is my autoencoder working compared to like off the shelf, like SZ or Z-checker. So what we did is we ran a bunch of analysis for them and then try to see how we can match them, because they were getting compression ratios of like 300x. So we started to run with SZ, ZFP, with different modes. And then we saw that, okay, let's see what are the different things. So this is for small scale, medium scale, and large scales. And we can see from this analysis that most of the time, using the autoencoder does not really achieve a much better result than just using SZ. So essentially, for the autoencoder, you need to go and train the autoencoder, which takes quite a while. And once it is trained, it is fast. But right now, their autoencoder probably needs to be improved a bit more, because they could just have used SZ and got essentially the same result as the autoencoder. So another example is using Hack and Cosmology. So here we use like a bunch of different compressors, And what we tried to do is we tried to evaluate with these different compressors, it's like what is the power spectrum ratio that you are getting. And what we see is for many algorithms, you tend to get a good compression ratio, but for one of them, it's like here we saw that SD probably like compressed a bit too much, and then the compression ratio was like the power spectrum deviation was a bit too much. And then you can go and tweak the amount of things that we use, and then see that, okay, we can tweak the different parameters and choose the best one. For the asteroid impact dataset, what we try to use is we try to use sampling. Compare sampling with different, again, error-bound lossy compression method. And what we saw is for kind of like roughly the same amount of compression ratio that you would get from sampling. Again, here we can see that SZ, this is the result for SZ. SZ is probably like as, here they just wanted like a visual analysis in VN. So here with SZ, you get pretty much like nearly an identical image to the original, compared to like with sampling, there was like a lot of data loss that had happened. So these are things that Foresight allows you to do. So it is of use to the scientist because it will allow the scientist to know, it's like, okay, you can try a bunch of different analysis data reduction methods, and then they can validate which one works best by running their analysis. And also it could be also useful to compression developers, because once you run your analysis, instead of just running MSE, PSNL, and things like that, you will also know for the scientists that you're working with, whether this type of compression makes actual sense to them, or whether you need to tweak it to compress less in some areas or compress more in some areas.
1 minute.
Okay, so to conclude, so what the aim is to like build trust in data reduction techniques, which is essential for adoption, and also allow scientists to evaluate their data, and also allow researchers to target what scientists want. So this is the link to the GitHub website for it, and also there's a paper, there's an SC paper that was published in 2020 about it. Thank you.
We have time for maybe one short question if someone would like to ask a question. Seeing none. Oh, question from Shang, something about the is this the asteroid 3D data set?
Yes, it's the asteroid impact data set.
Okay. The next presentation is going to be given by Katrine Heitman, but the slides will be presented by Pascal. So at this point, we'll go ahead and transition to that presentation.
Thank you very much. And thank you for giving us the opportunity to talk about data compression for HACC during this session. And actually, Pascal will talk in the second half of our presentation. You have heard already quite a bit from Pascal in the previous presentation about our challenges with regard to data sizes. What I want to do in the next couple of minutes is just put some more numbers directly to our problem with HACC. What you see here is an image that we produced in post-processing, actually after we ran a very large cosmological simulations, and then we populated it with galaxies to make it really look like the image from a telescope that actually does exist, the telescope. So there's a lot of information, obviously, from the simulation in this picture, and not just snapshot information, but time evolution simulation. And a lot of data is required to actually generate these kind of images that can then be analyzed by the cosmology community to see how well their pipelines work, for example. If you go to the next slide. What I want to talk about a little bit is the cosmological simulation data that Pascal described a little bit in the previous talk, but more from now as a scientist perspective. So in these extreme scale cosmological simulations that we carry out with HACC, and HACC stands for Hardware Hybrid Cosmology Code, we simulate the evolution of structure in the universe. And we need to provide precision predictions for data analysis tasks to the to analyze the observations from very large surveys. And what you see here on the right on the image is the time evolution. This is actually a picture that was generated from an output from Summit. So we used the full Summit machine for the simulation, but the output that you see here is actually just from one rank. The simulation evolved more than close to 2 trillion particles. And you see that we go from a very smooth distribution in the upper left to a much clumpier universe in the lower right. And in order to generate the images that I showed on the very first slide, we need to follow the structure at each and every time step. That's very important. So the time evolution tells us what kind of galaxies live in our universe. So this is obviously a very challenging task to track the evolution in that much detail. So if you evolve 2 trillion particles, you get a snapshot size of the order of 100 terabytes. You need positions and velocities. And in order to make these detailed analyses that I described, you need hundreds of snapshots. So the raw data size from one simulation is in the tens of petabytes. And then you have to remember that we don't run just one simulation, but we run suites of simulations because we want to investigate different physics in the simulations. So that is obviously a very, very big challenge for us because we cannot store that amount of data for long term on the big systems. If you go to the next slide. So how do we deal with this challenge? So one thing is what we can do is we can run in situ analysis. While the simulation is running, we do analysis tasks to reduce our data. The problem that we have run into several times now is the data is very science rich. And while the team that is running the simulation might have very specific science goals, the community has many, many more science goals that they could do with the simulation outputs if we just had stored enough information. And as I said, it happened to us several times that community members asked, do you have stored specific properties of the halos, for example, that Pascal mentioned, which are the structures, these clumpy structures that you see on the right in this image. And then we had to say, no, sorry, we did not. And so if instead of, so we will continue obviously to do in situ analysis for a first pass, but if we can store more data, more analysis will be available later on. So that's very important. What I also show here on the right is, again, you see in blue the structures. So the high overdensity regions are the halos. And we want to do different measurements on the output. So some measurements are directly done on the particles. So cosmology simulations are particle-based simulations. So you get something like the power spectrum that Pascal mentioned. Some others measurements are on the halos. So we identify the structures in the simulation and their time evolution. And for all of these, we need very precise measurements. And so using lossy compression will help us to reduce the data very drastically, but we also have to ensure that the data products still require have the required accuracy, as Pascal mentioned in his talk. And the flexibility for the compression approach is very important. So some data products might be compressed much more than other data products. And so that is where the exascale compression approach really comes into play. And I'll hand this over now to Pascal.
Thank you. So here what we can see is like some of the hack data, like Katrin showed before. So for the hack data, hack is basically like a bunch of points. So you have like position, then you have velocity, then you have a bunch of other different properties. And then from that, you also, what hack also generates is halo catalogs. There's basically like some properties of the halos that you have, and then it also stores different like particles for the halos, like for some of the halos, it will store like a bunch of like particles for especially the large halos that the scientists will want to look at, for example, some of these here. So if you try to do lossless compression for hack, for a position compression, you get at most 2x compression, and which is like not very good. For example, for the mass, you can get like a bit better compression. Sometimes you can get up to like 4x, but then if this is like using BLOSC and different modes. So if you get like up to 4x, the throughput might be like very, very low. So very often like the default setting will get you like at most around like 3x, where you get like reasonable throughput for compression ratios. If you're compressing like halo ID, which is kind of like an integer parameter, this one you can get quite lucky, and you can get like up to a bunch of like up to like 100x. But for floating points, which is the type that you get most of the time for most of the data, it is relatively low. And so we want to achieve a bit better than that. So if you want to preserve information for a power spectrum, like mentioned before, like a maximum error of 1x is required. And we can achieve that like pretty easily. For example, using SZ, we can get like a 5x compression ratio while keeping a maximum event per X spectrum to like 0.01. But where it gets a bit trickier is the halo properties. There are like two types of halos that the scientists are looking at in HAT. There's like FOF, friends of friends, and the spherical overdensities. So the spherical overdensities is, for example, here, this is a graph that I plot for spherical overdensity, and there are like different metrics, like for SZ at 0.015, 0.1, 0.005. So as you can see from this graph, which has been for the different halo masses, for like large halo masses, most of the time, it is kind of well preserved. But as soon as you try to do like FOF, the friend of friend, then suddenly it gets like much harder. For example, here, this is a graph of original, and then you see as you compress with SZ 0.015, and then 0.01, and then 0.05, things kind of like move all over the place. And sometimes you can get like changes in the halo size for up to like 24% change, which is like quite big. So what is happening here? Oops. So what is happening is when you do like the FOF halo finder, so sorry, this is FOF halos are hard to preserve. So what is happening is the distance between the friend of friend halo finder is basically the distance between the 2 points. If, for example, this is a point, this is the structure of a halo before compression, and these two halos are linked by this kind of like bridge here. And this is kind of a linking length. So essentially, if the two points are within a certain distance called the linking length, they are part of the halo. When you do lossy compression, that point might have moved a bit. So it moves just a bit outside the linking length range. And suddenly, instead of having one big halo, you have like two different halos. So what does that represent in compression? So before compression, you get like this halo and that halo. And suddenly after you've compressed, what happens is you just get like this halo, and that halo has disappeared from the picture, because now it considers this halo, because it has moved a bit, a completely different halo. So when that happens, it becomes an issue. Sometimes here, this is a case where one halo like becomes like two halos, but there's also a case where two halos become like one halo. And to be able to preserve all of these halos at the right level is kind of like very, very tricky. So before I showed in the talk, in the previous talk, that I was using like Foresight to be able to do a bunch of analysis, but sometimes like just using Foresight and doing like just like standard analysis is not enough. What we need to do for HACK is essentially, this is like basically Jupyter notebooks and analysis and a bunch of different analysis that we run detecting where is the position of a halo previously, what is the position of a halo now, what has changed, because it took us quite a while to determine why have the number of halos decreased in some cases. And in the case here, sometimes the halo has decreased by like 24%. Essentially what this means is like suddenly a halo which is attached, a smaller halo which is attached to a bigger halo might have just like disappeared suddenly. So there is still a lot of work that you are trying to do on that, like trying to see, oh, could we use, for example, like a topological analysis to determine that this is kind of like a weak bridge that we need to preserve and find ways to maybe target compression in different regions and having different amounts of compression. For example, this part is fine to compress heavily, but maybe this part, this is something that we want to compress less. So there are many things that we need to look at if you want, especially to preserve the different halos.
5 minutes.
Okay. So also, there is also NIX. So in the ExaSky project, there's also NIX, which is a cosmology simulation, and NIX uses an adaptive mesh AMR approach. So when you have an AMR, you have AMR data, there are like very, very few ways to actively achieve good compression for AMR data. Because very often what people do is they just, what people do is just like take the data, convert it to like a data stream, a 1D data stream. And once it is a 1D data stream, what you do is just compress the stream. When you do this 1D data stream and you compress it, you kind of like lose all the 3D properties of the data. And this is something that compressors like SZ can exploit. So this is some work that Darcy has done, and this has recently been accepted to HPDC. So what he's trying to do is trying to create a pre-processing approach to the data based on the data density before compressing. So essentially what he has is like once he takes the data, he kind of like split it into different ways, or classifies them differently based on low density, maximum density, and minimum density. And for each of these different approaches, he has a different way of preconditioning the data. It's like if it's a low density, strip out the empty regions because you have a bunch of zeros that you don't want, which represent like voids in, for example, in a simulation, or medium density, then you have to find the then he creates an adaptive K tree. And for high density, we kind of like pad some errors, pad some regions. And once per region there's like padding, then there is like better compression, because you don't want a sudden drop from like, oh, this is the data, and now suddenly this is 0, and this kind of confuses many other predictors. So based on that, he manages to achieve, like, if this is just using a 1D native approach, he manages to have a much higher PSNR for kind of the same bit rate. And essentially, that's all from me. Any questions?
Thank you, Catherine and Pascal. Are there any questions? I don't see. Oh, Hanji is asking, do you compress the Halo data to reduce the message size for Halo communication? If so, how much speed up do you think you can get from this?
So there are different approaches that we are looking at. For the Halos data, we are still trying to look at that, because we are mostly focused right now on compressing the raw hack data. Because this is a part that once you compress the hack data, we can like do a bunch of things. But for the Halo data, we have not really just looked into that yet. But this is something that we are looking at in the future.
Any other questions? Going once.
Just to add, and I'm not 100% sure that I fully understand the question, but the Halo communication between time snapshots is actually done right now in post-processing. So we store a lot of information from the Halos, like the particle IDs, to enable that. We do that because it's easier to identify a Halo at the very end and then track its formation backwards in time, rather than doing this forward in time. We tried a lot of approaches to do it forward in time, but it just is very, very difficult. I hope that answers a little bit more of that question as well.
Well, thank you, Catherine, and thank you, Pascal, again. I believe I have the next talk.
Yeah, so I will take over now the chain of this session. And as you have probably understood, in fact, we have switched from the compression tools, the compressor and the analysis tool, to the application. And so we had the first talk on hack, and the next, or ExaSky, and the next talk will be presented by Robert, and this will be about ExaFL, or crystallography, from Slack.
So as I said, I've already introduced myself, but this is work that I've worked very closely with Chunghong Yu from Stanford National Accelerator Center. Well, I have learned a lot about crystallography over the course of this project. There's definitely some things about crystallography that I don't know. So I'm, to a certain extent, going to be pitch hitting today. So first of all, what is serial crystallography? Why do we care about it? So the first question is, scientists use serial crystallography to understand the atomic structure of proteins. And this has many applications, from the domain of physics to the domains of material science and chemistry, biology. Like, there's a bunch of potential applications for understanding the atomic structures of things. And fundamentally, the way that this is done is there is a very high resolution detector, which receives basically diffraction patterns from a stream of nanocrystals containing these proteins that are injected to the X-ray beam line that is going to be produced. Where compression comes into this is that the volume of data that is produced from applications like this is simply enormous. With upcoming systems like LCLS2HE and APS2, even if you had a exabyte of storage capacity to store the raw data, if you ran this system for more than 12 days consecutively, you would exhaust all of the available storage space. So this leads us to the process of considering, okay, well, how do we compress? How do we process this simply enormous volume of data? To better understand how we do that, it's important to understand a little bit about how crystallography works. So you see the image on the right. This is a visualization produced by a tool called Piece of Cake, which does some analysis for crystallography for us. And the first kind of steps that it does is it identifies what are called Bragg spots. These are these cyan dots that you see in the picture. And these are essentially not just individual bright pixels, but pixels that are bright and have neighbors who are collectively sufficiently bright. So these kind of bright pixels and bright spots help us when we perform indexing to identify kind of the collection of peaks, even if we don't observe the peaks in any particular image that comes off the detector. Once we have that, we then merge multiple events together into a 3D volume, and then we perform a process called phase retrieval to actually retrieve the actual electron density. The key part to kind of remember from this discussion is that the last stage here, synthesizing the electron density, that's where a lot of the meat of the scientific analysis comes from. That's where you really get to understand the compressed data, but it also is the part that is most easily distorted if you're not careful in how you apply lossy compression. Over the course of our work today, we're going to be talking about two specific sub-methods within serial crystallography, which are molecular replacement and single wavelength anomalous diffraction, the latter of which can be thought of as a more difficult problem where you don't necessarily know the particular structure of the chemical beforehand. So what has been done in the space of serial crystallography for compression? One area that is being actively thought about is this idea of non-hit rejection. So as I said, you're injecting these crystals in front of the detector. There will be certain snapshots from the detector where no peaks actually are detected, where the X-ray does not intersect with any crystal particles, therefore there's no diffraction. And when you do this, you can actually reduce the volume of the data set rather dramatically if you throw out detection events that have very few Bragg spots in them. Some other techniques that have been tried have been things like lossless compression, deflate 3, GZIP is another name for this kind of a method. Some people have considered wavelet transforms or things that are vaguely based off a discrete cosine, such as JPEG 2000 or JPEG XR. Some people have even tried SZ or rounding methods to potentially address some of these concerns. But each of these methods kind of leaves us wanting either in the amount of compression ratio that we can possibly recover, or in the quality of the data and being able to reconstruct the electron densities that we care about. At this point, it's worth talking a little bit about the data processing system that will be used in these systems. And if we're looking at LCLS2HE, we have a detector that reads off approximately 1 terabyte of data per second. That is a scary amount of data to come at in any particular point in time. But unfortunately, that's not the worst of it. So the data that streams off the detector comes in as a series of uint16T, so 16-bit unsigned integer data. The first thing that is basically done as soon as this data is read in, it is converted to 32-bit floating point data, which is what's called calibrated to account for differences in the panels and other weather conditions and things that may be going on at any particular point in time. This effectively doubles your input data stream to 2 terabytes per second. After which we perform peak finding on the calibrated data, where we can then perform non-hit rejection. And then we're left with a stream of approximately 500 gigabytes per second that needs to be processed after we've performed all these other steps. And what we need to do is we need to get it down to the maximum bandwidth that the parallel file system will support, which is approximately 100 gigabits per second. as I kind of teased earlier in the morning session, the approach that we're going to do for this is called Roy-bin-SZ, region of interest plus binning with SZ compression. And what this will allow us to do is basically separate the important aspects of the image. These would be the Bragg spots that we've identified during peak finding from the background information. And there's a couple key things to recognize here. One, as a fraction of the overall data in each event that is being passed to the compression algorithm, peaks represent a relatively small fraction, less than 1%. The other thing that's important to know is that the background information is very, very noisy. It's very difficult to compress with existing tools, either losslessly or lossily. But there is information in the data that is really important. So I mentioned earlier this idea of Bragg spots, and some of the Bragg spots that you will observe are false negatives. So the detector failed to identify a Bragg spot. So we need to keep these bright, but still not bright enough to be labeled as a Bragg spot data available so that we can eventually compress it. And then finally, we'll apply binning. As far as the implementation, we're going to leverage the SZ3 interpolation predictor, which we find produces fewer artifacts with high error bounds. And we're going to utilize Libpressio to be able to swap out individual components of these as we develop advanced versions of, for example, SZ3 for GPU, or improve lossless compression techniques that could operate in the GPU. We're going to heavily optimize each of the portions of this using specific dispatch for different data sizes and dimensions, parallel execution for the region of interest selection, the binning, and some of the lossless and lossy compression stages. We're going to utilize Libpressio's zero allocation compression facilities to not allocate during the compression operations to save on latency and the variation in the latency. And then we're going to wrap all of this into an automated tuning framework, OptZ-config, that we mentioned this morning, to automatically select the specific configuration that works best for a particular data set, coming from a particular type of detector, as well as the hardware that's available. We're going to look at two data sets today. Forgive my pronunciation. Cibolitol strativiticin, coming from a CS-PAD detector, which is a slightly older style detector, if I'm understanding correctly. This data set has approximately 17% hits. So there's a fair bit of data that can be reduced using non-hit rejection. And then we also look at lysosine, which is an MR problem that we mentioned earlier on a slightly more advanced detector, the Jungfrau 4M, where with a slightly higher hit rate. The first thing we want to do is we want to tune hyperparameters in the algorithm for quality. So we're going to look at the potential of different binning sizes, how we represent the background data to the compressor, and different tolerance amounts. We chose these tolerance amounts based off the dimmest region that we observed in the image. 90 corresponds to the elbow of the intensities of the peaks, as you can observe in this histogram, and 45 is kind of a midpoint between these. From this, we identified the grid configuration, which was the best. We tried 9 combinations from this chart on the previous slide. And we identified the best configuration, and then we took the best configuration from each dimension and combined those and called that the greedy configuration. And what it's important to note is that the greedy configuration fails to reconstruct the electron densities as some of the previous models have. So paying attention to quality is something that's obviously going to be important. And when we evaluate this on a large number of crystallography metrics, we largely see an improvement, or at least we see a sufficiently close quality for all of the grids. The one anomaly is the CC ANO, which will obviously require some additional future study. When we look at a visualization of this, we can see a great degree of similarity between original and grid, whereas greedy is starting to smooth things out just a little too much. And when we look at that electron density reconstruction, we can obviously see that there are some holes if we are too aggressive and we utilize the greedy search. As far as compression ratios that we achieve, the grid search is 46.44 times smaller than the original and 154.18 times smaller if we additionally use non-hit rejection. So we're achieving relatively high degrees of compression here. And remember, this is the harder of the two problems. We also did the same thing with lysosine using molecular replacement, which is somewhat of an easier problem. And the data with this particular detector, after we apply our grid method with Roy-Bennett Z3, we get data that's 196 times smaller or 631 times smaller if we additionally use non-hit rejection. We can then automatically tune both our algorithm and variants of our algorithm using opt-z-config to select the highest configuration allocation of threads within the different aspects of the parallel algorithm. Couple of key observations. One, we don't allocate all of the threads to MPI ranks. So it's actually good to not use the full 40 cores that are available on this machine for MPI ranks. We want to instead use approximately 30 ranks per core. And that the specific allocation of threads differ from compressor to compressor. So it's worth doing this. Additionally, which was kind of a surprising result, is that it does choose a configuration with oversubscription of the 40 cores. And this can be accounted to the fact that we're not using all of these threads at all times. And then we additionally see benefits for larger chunk sizes. I will kind of cut the remaining talk a little bit short because we are running out of time on this talk. But we do see a basic linear scalability, and we can meet the bandwidth requirements with approximately 55 to 73 nodes. We may be able to get that down even further once GPU compressors are slightly more mature. When we look at our method in comparison to both variants on our method, as well as existing lossless and lossy compression techniques, we see that we consistently have some of the highest compression ratios available at very high compression bandwidths. It's kind of interesting to note that Roy-Bennett ZFP performs very well in terms of bandwidth, and that's in part because it's using the zero allocation compression support that I mentioned earlier. So in summary, Roy-Bennett Z3 allows us to adapt to new hardware compression methods as they're developed and achieve very high compression ratios of 196x or 46.44 x when we're not using non-hit rejection, and even higher when we do use non-hit rejection, all while maintaining the scientific integrity of the data. At this point, I will stop and take questions.
Thank you, Robert. There is no question on the chat. Is there a question that people want to ask? I can start, but we have just 30 seconds, so maybe you can answer quickly. Do you see other application than crystallography for this data reduction technique?
I do. So I think there's definitely opportunity to use this for things like preserving critical points or other sorts of features of interest within data sets. So there's definitely some opportunity for exploring this topic more broadly. To answer Kui Gong's question from chat, we look at rectangular regions of interest in this particular application because that was the easiest thing to implement, but the method itself is not tied to that, and it's relatively easy to swap out with a different region of interest extraction and restoration program that would use non-regular regions.
Okay, thank you, Robert. I think we need to switch now to the next talk. Thank you. So the next talk will be presented by Danny Perez and also I think Kai, and this is about molecular dynamic and the MDZ application or compressor application to molecular dynamic.
Thanks, Frank. So I want to thank you and Chang for the opportunity to present our results today. So I'll present the introduction, and then Chang will give the technical the technical details on the work. You can go to the next slide. Okay, next one. That's fine. So we'll start with the overview of the application area. I'll say a few words about Exalt, which is the project that I lead, and then Chang will go into technical details of the compressor that they developed for our microdynamics data. Okay, so molecular dynamics is a very simple numerical method. You basically solve the classical equation of motions for a bunch of atoms in a box. So you have to specify what we call a potential, which is basically an expression that gives you the energy of the system as a function of the position of the atoms. And then with this, you can compute the forces acting on your atoms, and you can basically just time step your atoms forward in time. And what you get is a fully resolved movie of what the atoms are doing as a function of time. So what's coming out of the simulation is a set of atomic positions and velocities as a function of time. So there was supposed to be a little movie here showing you what a typical MD run looks like, but oh, I guess it might be, no, it's not working. Anyway, doesn't really matter. But just to give you a sense of the systems, there's many different flavors of molecular dynamics out there. Some people do biology, chemistry, or materials. So in Exalt, we're mostly interested in hard materials, which are kind of crystalline and very well organized, like you can see the cartoon here, except for some defects. And I will come back to this aspect in a few slides because that turns out to be quite important. Next slide, Sean. So EXALT stands for exascale atomistics for accuracy, length, and time. So as this suggests, our goal is to give the users access to as much of the accuracy, length, and time simulation space as possible. And some axes are harder than others to scale along. So molecular dynamics traditionally uses domain decomposition to parallelize. So it weak scales very well, but it doesn't strong scale. So if you see on the picture on the bottom right there, that there's this kind of big region at long time scales and relatively smaller systems that is inaccessible to traditional MD because you're communication bound. So one of our big focus in Exalt is to develop methods that will try to bridge that gap. So try to push simulations towards longer timescales and not so much focus on the very upper end of the system sizes that we could run on the machines. Next slide. So that being said, there's different points in that simulation space that we're interested in running. So in green, you see kind of a largish system. Again, we're not hitting the memory limit of the machine, but it will be millions to trillions of atoms. And the goal is to develop methods to push this to the right to longer timescales. So even if we kind of save infrequently, we might have something like tens of thousands of frames that we want to save during the simulations. So this data sizes that we're talking about might be terabytes to petabytes. And in blue, it shows another regime that we're quite interested in, which are for much smaller systems, but pushed to much longer timescales. So hopefully close to seconds on systems of thousands to tens of thousands of atoms. And in this case, we might save something like 1 million frame. So that gives us sizable amounts of data, but nowhere close to where we would get by running closer to the trillions or billions of atoms limit that you see on the top. Next slide. So something that makes our data specific to the application regimes we're after is that, as I mentioned, we're interested in the hard materials. So most of the configurations will be crystalline configurations, but the parts that we're interested in are the defects. So anything that goes off lattice, like you see a big helium bubble there with the dislocation line popping out, and there's some surface defects that appear on the surface that you can see in gray. So these are the features we're really interested in resolving. And also these systems in a spatial temporal sense, they're quite stable very often. So you would have atoms that tend to vibrate around equilibrium positions for a long time. And then you will have a discrete set of jump that brings you to a new configuration where you might get trapped again for a long time. But that's not always the case. So some parts of the system will evolve quickly. Like, for example, the helium bubble you see there is more liquid-like inside. So you might have parts of the systems that evolve very fast, some part of the system that evolve very slow, and some mix of crystalline and non-crystalline material. So in terms of accuracy, we can deal with, we can tolerate small losses on accuracy, but what we want is to preserve the topology. So we don't want to compress so much that we cannot tell, or that we mislabel positions where we identify defects in our lattice, because this is really the defect behavior is really what we care about. So we don't need super high tolerances or for the compression, but preserving the topology is really important. Then I will hand it out to Cheng, who will tell us about the detail of the compression algorithms they came up with. I think you're muted, Cheng.
Okay, thank you very much. So, okay, let me talk about the MDZ, a kind of an urban lossy compressor we developed for molecular dynamic data sets in particular. In this slide, we demonstrate the compression pipeline of MDZ and where it is in the whole simulation. So you can see that without loss of generality, the MD simulations will generate a bunch of the data, and the data will be put in the buffer. MDZ will read the buffer and perform the compression, and after that, it will store the data to the compress the data to the disk. And in the MDZ, we have 4 stages, which is very similar to the standard Z compression pipeline. What is the most the key difference between MDZ and the Z2 is that we replace the previous prediction method by a new one, which can significantly improve the prediction accuracy such that the compression ratio can be improved in turn. Okay, so in fact, the key idea is to improve the prediction accuracy based on the particular patterns observed in the MD simulation data sets. Basically, we observed the 2 very interesting patterns in the molecular dynamic data sets. One is spatial patterns. It should be spatial pattern. This is a typo. So basically, we observed that for some data sets, the values actually always appear at particular levels. Okay, it will jump from one level to another one. So, but the values are not exactly the same with each other at the same level. So we developed a so-called vector quantization method. That means we just use the particular levels, which is generally the mean value of the values at the same level to approximate the values for each level, and then we quantize the difference between the level and the particular values at that level. Okay, so yes, so as you can see that in this typical data set, we can observe there are only 4 levels for the data values in this data set. Okay, so this slide demonstrates how we implement this vector quantization based compression for the spatial pattern. Okay, another very important question to answer is that how do we identify the values at different levels, right? So we need to record the particular level number for each value. In fact, we observe that the adjacent data points actually are very close with each other, such that their corresponding level number are very close with each other. So we just record the difference between the difference of the level number between adjacent data points during our compression. So this can significantly reduce the overhead. Okay, so another very important observation is that for some data sets, the data are very smooth across different time steps. Okay, so in this situation, we will observe, we will adopt a particular time-based compression instead. And so this raises another question: when should we use the time-based compression, and when should we use the space-based compression? So we developed a adaptive method to select the better solution at runtime. The idea is pretty straightforward. We run the simulation with different time steps, and we will check the compression quality every 50 time steps during the simulations and make the decisions. Because we observe that the data features may not be changed a lot within the adjacent time steps. Okay, so this slide demonstrates the evaluation results. So we use redo distribution function to evaluate the results. And this is a very important metric cared by the molecular dynamics researchers. And we also compare our MDZ solution with other state-of-the-art lossy compressors, including SZ2, which is a generic compressor. And other compressors listed here are some compressors published in literatures for MD simulation datasets. Okay, so we can observe that MDZ can preserve the RDF perfectly compared with the original data set, and other data sets will suffer from more or less data distortions. Okay, so we also evaluate the compression ratios based on different buffer sizes for MDZ, and based on and also compared the result with other compressors. We can see that MDZ, as shown here at the red curve, had the best compression ratio compared with other lossy compressors, also based on different error bounds for different data sets. Okay, so let me conclude our work. MDZ, based on our experiments, have the best rate distortion in class compared with all other state-of-the-art lossy compressors for MD simulation data sets. And MDZ has much higher compression ratio than other compressors with the same error bound. And it had been integrated in LAMPS package, and the LAMP package is a very important module used by EXALT project. And in the future, we will further improve the performance by optimizing the code implementation. Thank you.
Thank you, Sheng. So we have 2 minutes for the question. So maybe I will start with a question for Danny. So I think MDZ was designed for material. Can it be used for other type of molecular dynamics?
Yes, I think so. But the spatial correlation and temporal correlation aspects will be significantly stronger in hard materials. So it's kind of tailored towards our emphasis on long time dynamics and on systems that evolve very slowly. If you have systems that are way more dynamical, like just a liquid, it's unlikely that there will be so much spatial patterns there to exploit. So crystallinity is a big importance for the spatial part, and the kind of slow evolving dynamics is important for the temporal part. So there's probably other problems in this class where it could be used, but like in biology, for example, I think it's unlikely that you're going to see such nice results.
Thank you. I think that's important to clarify that.
Yeah.
Is there other questions? In fact, we are 10 seconds before the end of the talk, so I think we will stop here. Thank you, Sheng. Thank you, Danny. And so now we move to the next talk, which is EQSIM, and it will be presented by Hongjung Tang from Lawrence Berkeley National Laboratory.
Okay, can you hear me?
Yes.
Good. Hello, everyone. I'm Hongjung Tang. I'm a computer scientist at Berkeley Lab. Today, I will be talking about using compression in our large-scale earthquake simulation project. So our project is called EQSIM. It's the ECP application development project, and we are trying to develop a framework for regional scale up to structural simulations. And our project aims at answering two main questions: what is the distribution of ground motions, and what is the distribution of in-structural risks? So for the first question about ground motions, we do a regional scale, usually the San Francisco Bay Area earthquake simulation, and it will be run on supercomputers like Summit on Cori, and at very large scale, and it will produce a time history of velocities and at different locations on the simulation domain. And using this data, which can be very large, and I will talk about more details later. Using those simulation records, we do further analysis and visualization to simulate the infrastructure, for example, a 20-story or 40-story building, how they react to an earthquake event. And then we can get a distribution of infrastructure risk map, like shown in the bottom right figure. So before we have compression in the EQSIM workflow, for running an application, we have to manually calculate or determine a few locations where the seismologists or structural engineers are interested in, and then specify them before we run the application. That is mainly because usually a large-scale simulation run produces a lot of data, and without compression, we were not able to save all of them. So on the, as you see on the left figure, those gray boxes were the interested locations that we used previously for having them as the output. And this is rather impractical for many reasons for a really useful analysis. For example, we often found our team members, they once they started their analysis of an earthquake scenario, they often may need more data than they initially thought. And since those data were not wrote or output from the simulation, they do not have the data, so they will either abandon those tasks, or we have to run the simulation again, which is pretty costly. And with compression, specifically with lossy compression, we were able to significantly reduce the data size and allowing us to save the data from the entire domain or every grid point, either on the surface or down to a certain, for example, 150 meters depth for data analysis. So on the right part of the figure here, I'm showing two typical analysis types. One is called weak coupling, the other is called strong coupling. The weak coupling takes the ground motion time history of one grid point and applies to a building and see how the building shakes when an earthquake happens. And for the strong coupling, instead of using just the motion from one grid point, it uses a 3D subdomain of motion values and then apply those to the buildings and see how the building reacts. So in our project, we use HDI5 format as the storage format, and with HDI5, and we also use this CFP compression, we were able to compress the data and reduce the size pretty significantly. And in particular, we tried a few CFP options with different accuracy modes. We found for the lower frequency, like 5 Hz simulation, the CFP accuracy mode with 0.1 seems to satisfy our accuracy requirement. As you see on the top left part, comparing the uncompressed data, the right line, and the CFP compressed data with the black dashed lines, there is no visible difference that can be seen on with compression. So that is a good thing. And also with CFP compression, and our team members often use Python to access the data. It is very straightforward to use. So they can just install a Python package called HDI5 plugin, and then just by adding one line of code to their existing Python code, they can read the compressed data without any other changes, as if the data was not compressed. And on the right-hand part, I show this is the visualization of our one earthquake simulation. That because of compression, we are able to save the entire domain, and we are able to make visualizations for the entire simulated domain. So that is really helpful for our project. So with compression and HDI5, there are actually a number of tuning parameters for the total I/O performance. So there are tuning parameters at application level. For example, how much data do we aggregate before passing it to compression and output to file system? and what compression algorithm or configuration parameters we can use. And on the HDF5 level, there are things like chunk size, the HDF5 alignment, and whether to use HDF5 collective metadata operations or deferred metadata flash. And on the MPI-IO level, there is whether to use collective IO, and also there are some special cases like on Summit, where the default MPI collective IO sometimes is not behaving correctly, and we have to set the Romeo hints to manually enable collective IO. And on file systems, if we write data to parallel file systems like lossy, then there's a strap siding for our sets, and combining this last set of parameters, we do observe a significant performance difference, as I will show in the next couple of slides. So we have done a relatively not so small, but still not very big experimental runs just to see how using compression and how setting different set of parameters would affect the overall IO performance. So here the IO time includes both the compression time and the time spent to actually write the compressed data to the file system. So this is the result from 1024 nodes on Pori, and we have 8 MPI ranks per node, and we do vary the aggregation size, which is the buffer size. So we buffer either 100, 200, 400, 800 steps before doing compression and writing it out. And we also vary the chunk size. So this is 3D data. We have XYZ dimension, have 3 different settings, 60 by 60 by 32, 32 60s, 32 and 32 cube. And from all these different combinations, we do see that the total IO time, as I mentioned, includes compression and the actual write time varies a lot. So the worst set of configurations of the parameters and the best set of configuration parameters are have like 13 times performance difference. So that is really a big gap. And we are doing this experiment mainly just to find what set of parameters that works best. So and we do see some differences with the compression ratio also. So the uncompressed data for this the earthquake event will be 38 terabytes, and we do see after compression with CRP accuracy set it to 0.1, we can achieve a compression ratio more than 200. So that is very good, very helpful for allowing us to store more data. So next we have a big run on Summit. So this is our annual figure of merit run where we use where we use a lot of a majority of the Summit nodes. So we use 3,600 Summit nodes with 21,000 MPI runs, and we use a similar set of parameters with we are buffering every 800 steps, and the total IO time is meets our expectations. So it takes about 45 minutes to save the entire data set. And here, because we are doing a higher 10 Hertz frequency, we chose the CRP compression accuracy mode to be e to the -2, and we get a compression ratio of 103. And also the output size is totally manageable and compared with the uncompressed size. So in summary, the lossy compression helps us a lot to reduce the total size. It enables us to output more data and also reduces the total IO time. And another side note is setting suitable parameters across the software stack can impact the performance significantly. So that concludes my talk, and yeah.
Thank you. Let's see if there are some questions in the chat. I don't see questions now. I have a questions about the configuration for ZFP. So in one slide where you talk about HDF5 and ZFP, you mention 10 to -1 or 1E -1. I think that's not this slide, but the slide before that, one of the slides before that, this one. So can you comment exactly what is the error bound here? Is it an absolute error bound, a relative error bound?
Yeah, I think this is absolute error bound. Yeah, well, at least in ZRP, it is called ZRP accuracy mode.
Okay, okay. So that's yeah, it's interesting because it's a pretty high error bound. In fact,
yeah.
Yeah. Okay, and so one question about another question about the accuracy. So how do you assess the correctness of the data after compression? This is with this diagram, or do you have some other metrics?
Yeah, so basically the output is on this velocity time history, and we have done many experiments beforehand to compare the velocity values before and after compression at different earthquake with different earthquake simulations. And basically we conclude that for a lower frequency, like the 5 Hertz earthquake simulation, ZRP accuracy mode with e to the -1 is sufficient, but with a higher frequency like the 10 Hertz simulation, we need e to the -2.
Okay. Okay. But still, you get a very high compression ratio, still in the hundreds or something.
Yeah, yeah. So the main compression, I guess, happens because, so for a typical earthquake event, the first 1/3 and the last 1/3, they all have values very close to 0.
Yeah.
And it is only in the middle part where the earthquake actually starts shaking, then we have a lot of variations in the time series.
So is it something, I don't see other questions, so I'm asking a question that I have. So how do you, this is a simulation, and or do you also perform some measurements with probes and then try to reconstruct the profile of the earthquake? Maybe using some reverse time migration method?
Yeah, so we mainly for comparing the compression results, we just see how the difference between the compressed data and uncompressed data, and see the mean and max value, things like that.
Okay. So if I understand correctly, it's a forward simulation, right? You do the forward simulation and then you compare compression and not compression. Okay. Is there other questions? I don't see question in the chat. We still have something like 40 seconds. Let's wait just a little and see if some questions are coming. No. Okay. Well, then we can switch to the next talk, which will be the final talk of this session. And so it's about E3SM, and this is for climate simulation. And then the presentation will be done by Chiang Gong from Oak Ridge.
Okay. Could you see my screen?
Yes. Yes.
The slides?
Yeah.
Okay. Hi, this is Chiang Gong. I'm a computer scientist from Oak Ridge National Laboratory. Today, I'm going to give a presentation using MGARD for climate data reduction. First, in this talk, I will first introduce the data compression software MGARD, as well as the climate simulation code E3SM. After that, I will discuss how MGARD can be used to solve the data challenge for E3SM simulation. And in this talk, I will focus on 2 features of MGARD, the region adaptive and progressive retrieval. Before jumping into the details, I want first to articulate the goals for data reduction. First, the very basic goal is to reduce storage and I/O cost with large compression ratios. And meantime, we want to maintain both the raw data and their derived quantities of interest to use prescribed accuracy. And furthermore, for those who have concerned with lossy compression, we hope to provide an alternative data refactoring-based approach. This idea is to write data with high accuracy, but when the user read back, they retrieve the data as needed precision and resolution. I want to do a first recap of MGARD implementation. So MGARD is a lossy compression based on multi-grid linear interpolation and designed for error-bounded compression. It is analog to wavelet transform as it decomposes data into a collection of hierarchical components which are amenable to compression. As shown in the figure on the left, the richest information resides on the top, while the least information stays on the bottom. And such information layout structure make MGARD suitable for both data compression and data refactoring. So E3SM is the flagship code in climate community simulating the Earth and climate systems. Due to the memory consumption, a typical E3SM run requires around 2,000 nodes at Summit supercomputer, and parent mode can possibly reach central long in the simulation time. The simulation writes out time series outputs at user-specified frequency, like every 6 hours or a day or week of simulated time. The outputs are usually temporarily stored at local clusters and then moved to tapes or other long-term site, which will be used for different analysis in the future. The current high-resolution E3SM Earth atmosphere river E3SM atmospheric model could produce up to 400 terabyte data for a 1-year-long simulation. And the upcoming new climate model will generate almost like 50 times more data per time step than the current setups. So the data keeps rising. To reduce the data burden, right now the climate scientists usually convert the data precision from double to float or write the data less frequently. However, those approaches sacrifice the integrity of scientific findings. Since some E3SM data, such as the precipitation, are not uniformly distributed in space, this has motivated us to design compressors that carry region-wise changed error bound. Also, the same model variables can be used by different analysis code in the future. So some analysis code are simple and may want the compressors to deliver a sparse representation for accelerated processing, while other codes are complex and require the data to be very accurate. So ideally, the compressor should be flexible to support both cases. Our experiment used the 2D fields output from a high-resolution E3SM atmospheric model. Here we focus on 2 use cases: the tropic cyclone tracking and atmospheric river detection. We use them to illustrate region adaptive and progressive retrieval of MGARD. As shown in the left figure, the tropic cyclones, intensive circulant storms cracked by minimal sea level pressure and warm core. And the atmospheric river are shown here, like this gray shadow, which has a thin and long filamentary structure characterized by high integrated vapor transport. For both events, we use Tempest Extreme for feature analysis. So just like the cyclone and atmospheric river, features of interest usually are not uniformly distributed in the space. In such case, we hope to use more bits to store region of interest and less bits for the rest of regions. This figure shows the pipeline of our region adaptive compression. So this is the generic approach, which means we have no idea about what's the precise location of those features ahead of the compression. So the pipeline include candidate critical region detection and region-wise error control. The region detection try to find the regions where the data values are more fluctuated, as those are likely to be where those features are located. So we implemented by performing the adaptive mesh refinement on MGARD decomposed coefficients. User can define how large an RI to be selected by changing the parameters used by mesh refinement. And as you can see, those selected region of interest are highly irregular. The shape are highly irregular. And this figure, top figure, shows the theoretically how far and how much quantization error in the decomposed coefficients will propagate to its surrounding points after the multi-level recomposition. So based on this derived error bound, we use the buffer zone to cut off the error propagation, which show us the white region here. And using a specialized encoding, our approach don't save the mask of the different error bound, and data in different regions are actually decomposed and compressed together. This adapted compressed data can be decompressed the same way as single error bounded approach using regular MGARD decompressor. And this is a figure to show after the recomposition, how those error distributed. And we can see there's much less error in the what we call what we find in the region of interest. So first I want to show the result on the cyclone tracking. Template stream use 5 variables to find the tropical cyclones. In the left figure, we compare the L2 error measured in the region of interest. The error computed from the region adapter compression data are almost identical to those computed from the data compressed using the single error bound, which means we successfully cut off the cross-region error propagation. And they are all below the user-specified tolerance. In the middle, we show the benefit of compressing the RI and non-RI together. Here we use the RI mask detected using our MGARD decomposed coefficient plus mesh refinement as the input. And we compress the RI, this for the comparison experiment, we compress the RI and non-RI separately using different error bound, tau 1, tau 0. And we get the aggregated compression ratio and compared against our approach, the region adaptive approach. And as you can see, the benefit is quite obvious across all the 5 variables. And show in this figure, the right figure, oh, by the way, so the benefit mainly come from that we don't save the RI mask, and second, we find the data are better correlated in their original space. And finally, this figure shows that with the same compression ratio, the region adaptive approach achieves smaller error in the cyclone detection results compared to the data using the single error bounded approach. And this slide shows the region adaptive compression for atmospheric river detection. Compared to cyclone tracking, the improvement over the single error bounded approach is less significant. And this is due to 2 reasons. First, atmospheric river a long continuous region versus cyclones point-wise node features. So because our compressor does not know the location of those features, our adaptive approach must keep more data points into the candidate regions in order to not miss the desired features. And here, this figure, the left figure shows the original variables, and the middle one is the yellowish shadow, the atmospheric river detect using the temperature extreme, and these red regions are the candidate RI regions detected using our approach. So as you can see, we basically keep almost half of the region in order to not miss those atmospheric river. Also, we find the operators used to find that the atmospheric river is less sensitive to the errors in the raw data, which decrease the benefit of having dual error bound. But still, the region of interest is better. And one fear of using lossy compression is that in case the analysis code change and so as the requirement on the error tolerance, there's no way of going back to the original data. So here we want to present an alternative strategy. Instead of permanently reducing the precision, we refactor data into a hierarchical representation by combining MGARD multi-level decomposition with bit plan encoding. So given an initial user-prescribed error bound, we designed a greedy algorithm to select appropriate bits of coefficient coefficients at different levels. The advantage of using bit plan instead of error quantization is that the newly retrieved bits can be added up to the old representation to deliver a more accurate results. Such approach allows application scientists to write the very accurate data, but read back a sparse portion with needed accuracy. So in the following slides, I will show two use cases of progressive retrieval, which are retrieved with less precision and retrieved with less degree of freedom. Precision-based data retrieval allows users to retrieve less amount of data from storage. A research we are working on is to study how to retrieve the precision adaptively and when to stop. And here is a figure showing the decreased error in the contour analysis when we incrementally add up more precision to the raw data. And in this example, we stop adding more precisions when the analysis result did not change anymore. And here, this slide shows the resolution-based progressive retrieval. One disadvantage of the previous precision-based reduction is after the recomposition, the data will be expanded to the original dimensional space. But with MGARD hierarchical data refactoring, we can retrieve less degree of freedom by discarding the data at fine levels. Such approach does not only reduce the memory cost, but also accelerate the data processing because we provide a smaller data set. A research we're currently working on is to combine the region adaptive with the resolution-based data retrieval. And here example showing of this example of isosurface analysis on the velocity field of hurricane data. The upper figure shows the isosurface computed from the original data, and the bottom figure shows the data with about 30% of the region retrieved at 1/16 of the original resolution. And the visualization of these two analysis results looks almost identical, while the bottom one uses much less data points. And that's conclude my presentation.
Okay, thank you. So there is time for very, very short question. Is there any question? So there is a, I don't know if Robert, this is a question for Xian, is it? You are muted.
Yes, I was curious if there is an example of using this progressive retrieval API somewhere in the code that I could look at.
Actually, we have the CPU version.
Yeah, I figured it was the CPU version.
Integrated in the GitHub. That's in the GitHub.
Okay. If you could send me, because you have my email, you could just send me an email where to find the code.
Sure.
Any other question? If not, then we will go to the discussion session. Thank you, Chen, for your talk. And I will start sharing my screen again. So this is the last 15 minutes of this session, and in fact, you have seen many different things today, starting with the compression tools, the 4 different software that are developed in ECP for compression of scientific data. Then we looked at the tools that you can use to assess the error of lossy compression, but also repository where you can submit your data set, and that will be used by others, people who develop compressors in order to compare their techniques. We have discussed about the compressibility of data set. How can we imagine how much a data set could be compressed without necessarily using compressors, but just having an idea of how much it could be compressed. So we have looked at all of that. We have looked at application of lossy compression in different domains. So I would like to ask the people who have not talked yet, the participants, if you see something missing in this picture, something that maybe we missed, and that you think as a user or potential user of lossy compressor, you would need. Maybe this is in terms of trust, what tools you think would help to get more trust in the compressed data. So I would like to open the floor and see if some people have some comment about that. So shall I conclude that you are happy with everything that has been done and nothing is missing? Probably not. So is there any comments on what could be a good addition? Or is there any question that you would like to ask to the presenters that you didn't have the opportunity to ask so far?
Yeah, I would like to ask a question. You know, when these data sets are decompressed, in some cases, such as I'm trying to remember which one it was. If it was, for example, the last one when they're looking at the energy exascale Earth system models. Some of that data, like where you're trying to predict weather patterns, that kind of thing. You know, in that case, you can kind of visualize specific areas where you see changes in the model. You might not be able to associate those with some of the other applications, with something you can really understand, like weather. You know, do you find that the accuracy is really off enough that you really can't make any real predictions once you do the decompression or the compression?
So I think, Sian, this is a question for you. I don't know if you can comment on this. Oops, maybe we lost Sian, maybe it seems.
Oh,
no,
sorry,
okay.
I didn't have, I was looking the question in the chart. Could you say it again?
Okay, yeah. So what I was saying was when you compress the data for either one of these applications, you get some slight variations. Sometimes the variations is really large, but even when it's not large, there are some variations that can be detected in the models that you get in result in a lot of the cases. How critical is that to actually being able to predict something from the compressed data versus the actual data?
So the MGARD, the compressed data based on the multi-level interpolation. So the decomposed coefficient naturally capture the local variation of the data. And we use those decomposed coefficient as a metric to measure the data fluctuation. And you choose how much percentage of the total data coefficients you want to keep in those high accuracy region. And by changing that threshold, you can you can definitely change like how, if you want to keep just a very fluctuated region, or you want to keep more like less fluctuated region into the RI.
Okay, but how does that translate to, all right, so these predictions, I guess, are over time, and they're not really associated with any specific event that may occur like in the next day or two, you know, or like, for example, if you're doing hurricane tracking and you're trying to determine, you know, what the path of the hurricane is going to be. So,
So your question is how compression will affect this this prediction?
Right. How's it going to affect the prediction? Can, you know, people feel like, okay, my weather's going to be, you know, XYZ tomorrow or next year. We can expect, you know, hurricanes to come through here at a certain rate. Based on the decompressed version, how often is the decompress from the actual data is my question, or something like that.
So in my slides, the result I showed was conducted through using the 5 years cyclone tracking data. So I find that I just use one threshold for all those 5 years tracking. Like I keep the top 20 to 25% of the coefficients to be the high accurate, to be the RI region. And I have 75% of the cyclone tracks that exactly match with those detected in the original data. And for those 25% of the mismatch, the difference is very, very tiny. Like most of them are less than 1 pixel shift.
Yeah, so let me kind of say this a different way. So many of the compression methods, MGARD included, give the compressor of the data, the person performing the compression, the ability to specify mathematical guarantees on the data that's being compressed and then what it will be when it's decompressed. So having these mathematical guarantees can give you confidence on relatively simple metrics. When you start getting into more complex things like halo masses or crystallography data, where you're trying to compute these higher order analysis things like Z-checker, things like Foresight, things like opc-config start to play a role into helping the user infer what the answers to those questions may be. So for example, you might use opc-config to say, I want to compress this data, but I don't want my temperature prediction for the 10-year time window to be more than plus or minus 1e-6. Now, that may take you a while to find a configuration, but you could, in theory, ask the tool for that kind of information. And given enough time and resources, it could probably give you a good guess. Does that go in the right direction?
Yeah, that goes in the right direction, yeah. Yeah, so with like X-ray, with crystallography,
yep,
those kind of variations can really change maybe like the amino acid sequence to some degree, possible structure like that?
Yeah, so that's why we looked at the electron density reconstruction. So a lot of the lossy compression methods that had been used before Roy-Ben-Ez-Z didn't recover that information particularly well.
Okay.
At least not at compression ratios that were useful at solving the problem of the bandwidth concerns that they have.
Right. So then in some cases, those kind of small variations are okay. In others, it may lead to, you know, things that really prevent you from making the kind of determination that you really truly need to make.
Well, let me be a little more specific in the Roy-Ben-Ez-Z case. So in the Roy-Ben-Ez-Z case, it's not that, like, we could make the variations very, very small. We could choose to use a very not lossy compression. But if we did that, we would only get a compression ratio on the order of, say, 6 or 10.
Right.
And that doesn't meet other requirements that the user has. So the question is, how can we accept substantially more loss in order to get the compression ratios to something that actually meets the user's needs?
I got you. So we're really looking at what the user really needs in order to do what it is they're trying to do versus how to get the best data for the user necessarily, because they might have some limitations on
Yeah, so-
hardware, things like that.
Yeah, so the goals that we typically describe is that we're usually looking for in the context of scientific data compression is we're looking for diagnostically lossy compression.
Okay.
Now, or diagnostically lossless compression. So what we mean by that is we want to do the most compression that we can that could be lossy compression, but from the perspective of the analysis that's going to be performed after the fact, we want the decisions that you would make based off that analysis to remain invariant.
Yeah.
Right. Okay, thanks.
Yeah, I think the key word here is the preservation of science. That's what the user want. And as Catherine said in her presentation, in fact, you may have different users for the same data set. And so when you compress a data set, you may satisfy one user, but you need to be also considering the other users. And that's why progressive compression or progressive decompression is also important so that you can get more accuracy if you need. But of course, you cannot reinvent the accuracy that you lost, right? So you need to encode it somewhere. So I think that's the most important message here is that everything that has been developed in the context of ECP in terms of data compression, lossy data compression for scientific application has been done in the perspective of the user and making sure that we preserve science. This is really the most important thing here. And then, of course, reaching the other constraints, which are speed and maybe memory occupation also when you do the compression. So these are the different factors that we need to consider. I think we are very close to the end. Is there any other question? I think there was a long question from Chris. So I could not find the question in your text. Maybe you want to ask it orally.
Sure. Just basically, we use a lot of the tools that are mentioned and that are looked at by ECP. But as a system administrator to these tools, to the results, I was just wondering what I could glean from this awesome presentation on how to maintain or to shrink some of this data for storage and for transport to our other facilities and in other continents.
Yeah, so Chris, I responded to you just a few seconds ago in the chat. But the key kind of takeaway is that we want to make sure that we're engaging the users of these data sets to make sure that their scientific analysis and their simulation analysis and the other kinds of analysis that they're going to do are remaining intact. So most of the presentations you've seen today, with a few notable exceptions, are working with things that can be represented as large, dense, multi-dimensional arrays of floating point numbers. So to the extent that you have data like that, we can definitely work with that. Now, there are things that work with other kinds of data sets that may be able to take advantage of these things as well, especially with some of the recent developments in ZFP and MGARD, for example. But it's probably not something that would be applied at the facilities level, but something that the facilities might encourage the domain scientists to use, if that makes any sense.
Sure. That's what I figured. I just wanted to make sure I didn't miss anything. I did miss about an hour of the presentation and wanted to make sure I covered all my bases. Thank you.
Thank you. Well, this is just in time, so I would like to close now the workshop. I'd like to thank you, the participant. Thanks to attending this workshop or this breakout session, and of course, thanks the speaker and ECP for funding us and helping us to generate good compression tools for the application. Thank you.
Bye.
Bye-bye.